let me begin with some remarks on singularities. We talked about it last time, but I want to emphasize what's going on here. So, recall an interesting situation. You could start with an example. So usually we do this example in affine space. So let's look at this affine curve. So let me write here F because it's in affine space. Talked about it yesterday. I want to emphasize something about it. So this affine curve and you notice, let's call this function f, and if you are interested in singularities, you look at the set where df is 0. So df, what is df? It's 2z dz minus 3w squared dw. And so this set is just consists of the origin. And certainly this is then contained in the curve. So this is a singular curve at the origin. And I mentioned yesterday, it's a funny singularity. I just wanted to emphasize funny things that really happen. There's an easy map of the complex plane onto this curve. Namely, you just take zeta in the complex plane and map it to zeta cubed zeta squared, the way I've got it now. And you see actually that this thing is, of course, holomorphic, and it's actually a homomorphism. But it is not in any way bihomomorphic. We will understand that later on, but it's a homomorphism. Now, excuse me. Let's look at this thing at the projective version of this curve. So C is the compactification of this curve in projective space. In projective space, P2. We'll recall in the usual coordinates z is equal to z1 divided by z1. So the affine, these are the affine coordinates. It's a good exercise just to do this. And so we put the affine coordinates in the curve equation. We homogenize. We homogenize the I'm just talking about the singular curve. I want to talk a little bit about singularities at first. Just to give you an idea that you need to watch out. Very funny things happen. And it becomes a question quite often of delicate algebra. So you homogenize the equation. I just wanted to, it's a good exercise to do this just for fun, to wake up. So the equation, you start out with the dehomogenized equation, which is z squared minus w cubed equals 0. And then you clear denominators and you get the homogeneous polynomial, which is a silly one, z1 squared z0. It's a cubic. So this is the equation for the projective curve. The projective curve, what I'm calling here C. And just to tell you at least the way I think about this thing, the picture I would draw is this. So I always draw P2 like this. Here's Z0 equal, well, here's my origin. See, I divided by Z0. Back in the back here is always my Z0 equals 0. So that's what we had to do to compactify the curve. And if you compactify the curve, so let's see, you put 0 in here for Z0, that means Z2 is Z0, so Z1 obviously can't be 0 because it's projective. So back here in the back someplace is the point Z0, what did I say, can't be 0? Z2 has to be 0 and Z1 is not 0. Someplace, oh, well that's a corner, I'm sorry, but let's see which, that's one of the corner points here. So it's something like this. Right? I'm not sure which one. So, okay, so it's a reasonable curve, just intersects infinity in a reasonable way, I think. It's singular, and we do feel like it's a cusp singularity here, and maybe it goes something like this. What I wanted to comment about that curve, just to emphasize something I may not have explained correctly or appropriately yesterday, is that in fact this mapping, this obvious mapping here, let's call it a mapping pi, I don't know, let's call it the mapping phi. So phi extends, of course, phi as a mapping from P1 to this curve. Right? I mean, the origin goes to the singularity, if you like. Here it is, I don't know, I think the origin is probably, if the parameters, what is the origin? The origin here is probably that. And that's what we're calling 0. And then infinity would be this. And you can easily see this parameterizes the curve. That's the homomorphism. That's the homomorphism. So that means this curve is a copy of P1, but only homeomorphically because of the singularity. Okay. So we call, it says P1, you remember the function field of P1 is simply the rational numbers. So we speak of P1 being a rational manifold, and then we speak of this as being a rational cubic curve because it's just parameterized by P1 with this funny singularity there. And let me tell you why I think it's funny. I always think of these things in families, so I look at this in terms of the moving principle that I talked about yesterday. So you start with a smooth elliptic curve. So let's start with the Fermat cubic. So let's just start with the Fermat cubic. Now that's a beautiful smooth cubic, and we derive the genus formula for a cubic curve. This is a genus. I will be careful today. 1. Right? So, and I explain what I like to do here. I like to build a family. Let's build the family from our cubic. Yesterday I built family from between two smooth cubics, or two smooth things of the same degree. This is a family parameterized by P1. And let me put here this singular elliptic curve, singular cubic curve. So Z1 squared is Z0 minus Z2 cubed. And it's the same thing as yesterday. Well, this is the 0 point. Here's P1. And here is the point where that is 1, the other 0. So this is the point. This is the plane of zeta 0, zeta 1. And here we are parameterizing the simplest cubic curve of all time, namely the Fermat. But at infinity, over infinity, you have the curve I was discussing over here, namely this is infinity. You have the curve that I discussed here. So it goes from something of genus 1, you move it, this still has degree 3, but the genus has dropped, at least homeomorphically. Okay, so if singularities are involved, terrible things can happen. You see what I'm talking about? Okay. I tried to visualize this morning, maybe I'm a little bit too tired, but what must happen somehow, it'd be interesting just to visualize this on a computer, is
the pole getting outside and getting into the pole?
Yeah, I think that's right. The hole somehow is moving somehow to a boundary and collapses and then to a point, so you just have no hole anymore and just have that. That must be what's happening, right? So that's sort of an interesting, I just wanted to warn you what an interesting thing in the family of wonderful smooth curves, you have on the boundary something where the genus is even 0. That's the first thing I wanted to remark on. Second thing I want to remark on the question of Mihai yesterday about real submanifolds. It's so beautiful, I guess. So his question is about smooth, real, let's emphasize, so not complex surfaces, say column M, in P2. See? So you regard P2 as a 4-manifold, dimension 4, and this is a 2-manifold, and you ask the question, what is it? Now there's a stupid remark. Is you recall that P2 contains a coordinate patch for example, the one U0 not equal to 0, which is C2, and as a real manifold, that's R4. And R4, I'm just making some ridiculous remarks here. I could have answered your question yesterday with a stupid remark, but I'm happy I waited because then you can think a little bit more. So this contains R3, and this is our room here, and everybody believes that you can put a surface of genus G in our room. You see it, right? So, I mean, there's nothing going on here. Okay? So this is the answer to your questions you can always do. However, by the way, also non-orientable, because I think you can put, without self-intersections, you can put the real projective plane in R4. Usually you have to, or the Klein bottle in R4. Usually it has to go inside itself, but I think if you bring it into R4, you can do it, right? So really you can put anything here. The point is that since this R4 is topologically just a cell, so it's topologically trivial, this thing is topologically trivial in R4, and therefore it's topologically trivial in P2C. So in every sense of the word, whatever you think topology means, the topological class, for example, it is represented as in Durham cohomology, the differential form which is going on here, or the homology class, or whatever you want to call. This topological class, is 0. So this is the naive example is a stupid example because you put it in there in a stupid way. So the question is, can you put it in there in a topologically non-trivial way? So that was Mihai's question yesterday. I reinterpret his question as, can one embed, for example, M of genus, it's a smooth surface, so let's say orientable, genus, say 2, in P2, C, that's his question, topologically non-trivial. So as a non-trivial topological cycle, this is really the interesting question. And this question is...
Can you please explain a bit? I don't have too much knowledge of topology, but
I'm going to explain that.
What is the difference between...
Yeah, take the time, why not? I explain what I mean by that, okay? It doesn't hurt to spend 10 or 15 minutes on this subject. You see, when you study topology, it's the same as anything else in mathematics. These guys spend one semester telling you what Hausdorff means, and then they spend another semester building homology theory, and then you still don't know what the homology is going on in P2C. So I believe in the inverse procedure. Start with P2C and try to figure out what's going on. Okay, so I'm very happy to try to explain something. Okay. So let's take a detour into elementary topology. Let me just explain. So let's, for example, talk about singular homology. Okay. Whatever that means. Well, so what is, for example, a one-dimensional simplex is that, and a two-dimensional simplex maybe is you make a point and then you make that. You see how you proceed recursively to make simplex. Right. So a three-dimensional simplex is you take two-dimensional and then you take a point over it and do that. Okay? Okay?
What are the two lines inside the triangle?
This thing?
No. And
This thing? That means I'm talking about the region here. The suspension procedure, I fill out this stuff here. I fill it in. That's how you make a triangle. I'm making recursively elementary geometric figures. An interval, and then I take a point in R2, and then make the convex hull. And then I take a triangle, and I take a point in R3 and make the convex hull. If you start writing these down, it costs me much, you have. Okay? Now, so people have an idea here, there's some topological space X, and historically you want to piece together these things, say a two-dimensional thing, you start piecing together these things. Try to understand. This turns out to be possible to do. This is called simplicial homology, but in my mind it's difficult because it's a piecewise linear theory in some sense, piecing things together. And I mean, it works out maybe, but I don't like it, and I think it's much easier to understand something else. So you talk about singular. I'm a little bit naive here. I don't know why the word singular necessarily, why we use the word singular, but we talk about a singular chain of dimension K. And the singular chain of dimension K is a map. First of all, you say, I want a map of one of these things. So you take a d-dimensional simplex. So you take a d-dimensional simplex, SD, d-dimensional simplex. Oh, I'm sorry, k-dimensional simplex. Simplex, and you just map it into the space. So let's say X, you map it into the space, into X. I mean, that's what it is. It's a parameterization of this thing. But you just take any map, continuous. Okay? Any map. So I think this is a very interesting thing.
How do you define continuous? Like,
huh?
You need topology to define continuous.
Yeah, X is topological.
Okay, X is topological.
And maybe you get scared and you even assume it has some reasonable topology. For me, it's close to a manifold, so I don't worry. And so the object is phi. I think we can learn. I mean, you should always say we are doing mathematics standing on the shoulders of giants. And we're standing on the shoulders of some giant who went from elementary triangle. Riemann understood the basic topology of surfaces by just triangulations and putting things together and so on. So he really understood it. You understood the fundamental. But somebody had the guts to say, the courage to say, I'm going to consider all of these things. Okay? And not only am I going to consider all of these things, I'm going to consider formal linear combinations of these things. So a singular chain is a formal linear combination of such maps. Of course, each of this of dimension k. So this is a singular k chain. So you just think of putting these things together, but with multiplicity. And you will see very soon you have to have multiplicity. So,
Professor, what is phi I?
Again, phi is just an arbitrary map of a k-dimensional simplex into the manifold, continuous map. Phi I are just some of these. So these things here are as above. So continuous maps here. Okay? Then somebody had the courage to say, I'm going to consider formal linear combinations of these continuous maps. You will see when you piece these things together, you double up and all sorts of things happen. So you need to do that. So the original, I think the original idea of somebody was that these nj's should be at least, at worst, integers. So formal linear combination. Now there's a famous story. So let me tell you the famous story. So Alexandrov, the great Russian topologist, visited Göttingen many times in the 20th century before the Second War, between the wars. Alexandrov is his name. He's now dead, but he lived a long time, I think. Now, in Göttingen, there were really great mathematicians, I think you know, Hilbert and so on. But Hilbert was very wise and called to Göttingen the greatest young mathematician in the area of algebra, namely Emmy Noether. And she understood algebra, and she you see, for an algebraist, Emmy Noether, putting some formal linear combination here, she does that in her sleep. She doesn't worry. Even though she was incredibly calculational in her first works, she was a student of an invariant theorist in Erlangen. She became very abstract and developed all of the algebra here. And she had this friendship with Alexandrov. She visited him in Moscow and so on. There was a very interesting political discussion here also. I think she's a very good friend of Alexandrov. And there's this story, Göttingen, like many German cities, has an outer wall. Yes? And they walk around this wall, and after a while they walk around twice, and she started talking to him about that he was too naive, that you don't necessarily need here these things, and she convinced him by walking around the outer wall of Göttingen 2 times that usually you only need coefficients in Z2. Yeah. So, and maybe you don't need coefficients in anything, you need coefficients in some ring. Maybe it would be good if it's a field. Yes, this is a field, this is nice. But maybe Z is good, maybe some ring. It doesn't matter in some sense. Well, it matters, but I mean, maybe it's even interesting, but you should just think of this formally. Whereas Alexandrov and the Italian Betti, there are numbers called Betti numbers, which I'm going to talk about in a minute. These people really were thinking of just multiplicities and so on. So this became a formal algebraic subject. You look at formal singular K-chains. Okay. Then, of course, Stokes' theorem should be true. You don't see Stokes' theorem here. But Stokes' theorem has to be true. The motivating thing here is Stokes' theorem. Stokes' theorem has to be true, punct, comma, else. So Stokes' theorem you see, at the time of Emmy Noether and so on, with the discussion with Alexandrov, differential forms were not known. So this, they were known in some calculational way, maybe in dimension 2. I think you can fairly say differential forms were not formally written down carefully until Chevalier after the war. So Stokes' theorem is this. The integral around the boundary of something, of a differential form, whatever that is let's call this thing C. Either chain. Should be this. This is Stokes' theorem. Now, you certainly want to integrate over such an object. That means you want to pull it back by the mapping and integrate. So let me just, you see, if you hang out with physicists, you have no worry at all about doing everything I'm doing. I mean, you just do it, and you should. You really should. Don't worry about it. So you pull it. This stuff is only topological, and that's a smooth differential form. Who knows? Maybe we can make it abstract. We pull it back and integrate. So, I don't know. You pull it back. This should be the sum nj integral over the simplex sk of phi j of d omega, and this thing should be the
it's phi j
star, and this should be the same thing, only you have to pull it back to the boundary. So this should be I don't know, the boundary. The boundary phi j star omega sum over the bound, whatever this boundary. I don't know. They're very complicated here. I don't know what to say. If this theorem is not true, then this theory is wrong. Okay? You have to say it that way. This theory must incorporate Stokes' theorem. Okay? So this means these chains should be oriented chains. So you simply know if you have a tetrahedron, for example, or a higher dimensional thing, is sitting here in R3, and you have the standard orientation in R3, which it inherits, as does its boundary. The boundary orientation. We talked about this in my course last time, induced boundary orientation. Okay. So now these are oriented chains. Okay. And now you have to take the boundary of a chain. I see you starting to ask a question or not? You have to understand what is the boundary of a chain. Well, obviously, it is the boundary image of these boundary faces, right? But you better watch out for the oriented boundary, right? It depends where it is. So it's going to be an alternating thing. It comes from the fact that the boundary of an interval is this, I don't know, this thing with plus and this thing with minus, and therefore the fundamental theorem of calculus is true. The integral over the boundary means f of b minus f of a. That is Stokes' theorem, and you have the alternating sum over here. Okay? So, in order that Stokes' theorem is true, this must be true. Whatever true means. So that means that the chains, you look at oriented chains, so you look at oriented K-chains. Oh, no, what kind of chains do I have there? Yeah, K-dimensional. K-chains. With boundary, K-chain C, with this thing, boundary of C, the oriented boundary. Boundary chain. That's it.
Is it also a chain, the boundary?
Sure, because it's a formal linear combination with, that's one of the reasons you need negative integers also, right? Because it's the same.
Orientation.
Because of this orientation. Okay, it's the reason you really need maybe some reasonable coefficient ring or algebra or whatever you have. Okay. So you have the K-chains in X. I've always just admired so much our great giants that we're standing on their shoulders. I mean, it just takes amazing courage to say, I'm just going to look at all the oriented K-chains. And we have a boundary mapping.
But not all chains are oriented?
Huh?
Not all chains are oriented?
What kind of?
Not all the chains are oriented?
No, of course not. I mean, I can take all sorts of continuous mappings that are terrible. Okay. So oriented K-chains.
So then what it means to be oriented?
Don't worry about it. Maybe I don't need to take orientation, but I certainly need to understand what oriented boundary means. In the discussion, maybe I don't need to say orientation, but I'm thinking orientation, and I'm thinking that in manifolds. And I need the oriented boundary.
You need that because you need a simplex. You need to create an exact sequence, no?
Yeah, but that's some formal algebraic nonsense. The reason you need something is Stokes' theorem. And the reason you need Stokes' theorem to be true is because of orientation. And the key thing in life is the induced orientation. Okay? So I'm saying that really, maybe you can forget the fact that these simplices are oriented. I need the oriented boundary of that thing. That means I'm talking about the induced orientation. Okay, so, I mean, what you're saying here, you heard some words from somebody, that what you want here is a complex. That's a modern point of view, right? Okay. In fact, you do have it if you do this right. So you want a homology theory which says singular change modulo. You're asking if something is trivial if it's the boundary of something else, right? Right. Two things are equivalent. You saw it before. They're co-ordinate in some sense. Remember this homotopy, this moving argument I had. You have something on this end and something on this end. It's really, really important that the orientation, you see, the sum of these things is the boundary of this, but with sign. That means this is equivalent to that. Okay? So orientation has to be in this. Okay? Okay, that's homology. That's it. Now, I mean, so what? Right? This doesn't help you very much at all. But you start proving theorems. It's a good object when you start proving theorems about it. And one, well, for M, a compact manifold, then all of the homology groups are finite dimensional. All can. So all of them. Now there's a point here that everybody, when I take a qualifying exam, I ask him the question, he always knows, but then he knows nothing else, and so it makes me very mad. No, Latif, you knew a little bit more. You prove something called Hurewicz theorem, where Hurewicz theorem says, you see, Hurewicz theorem, yeah, let me take this is a big detour, I'm sorry, but maybe it's useful. An example of mapping something into a manifold is mapping in S1 into the manifold. Right? You can certainly make S1 a formal sum of intervals. I think you can make it very easily a formal sum of intervals, right? You can just see how to do it. Maybe with 2, right? You do that and that. Right. Okay. And everybody here understands, doesn't understand, but heard something about complex analysis in one variable, and all of these things you integrate over a curve and you get 0, and all of these residue theorems and so on. I want to emphasize here that is a stupid point of view. Residue theory and all of this is not a homotopy theory. Period, comma, out. It is a homology theory. The residues, one complex value, you can never measure homotopy. What you are measuring is homology. And the thing, and it's completely obvious that you're only measuring homology because everything is an integral. An integral is somehow dual to this homology. But what you do know is Hurewicz theorem, which says this. So the first homology is very close to the homotopy. It's the abelianized homotopy. Of course this is abelian. I mean, this is a quotient of abelian groups. Right. The homology of the puncture plane in 2 points is the free group on 2 generators. The homotopy. The homology is Z plus Z. Now, you see, when you integrate in complex analysis, you integrate over something, yes, and it's a mapping from, you're integrating from something to an integral, and it's completely obvious that this is a map into an abelian group, right? You're mapping, it's a functional. An integral is a functional with values in R, or something like this. So it's completely clear that this kills the non-abelian nature of the homotopy. So please, when you're thinking about complex analysis in one variable, for example, and somebody tells you about integrating over curves in some homotopy argument, please say to that person, that may be nice, but that's not the right point. Okay? It is a homology argument. And in fact, it's even less than a homology argument. It is a cohomology argument. Let me tell you why. Homology may have torsion. There is no reason that the quotient of two visiting groups is torsion-free. You will never in your life understand with a standard integral something that is Z2, right? Because it has values in R, or C, something like this. You will never in your life understand it. So what you're really doing is something dual to homology. You get something dual to homology, and you should see it. This is homology, defined correctly because Stokes' theorem is true, but it is a functional on homology. Okay, it is a functional on homology, and so you ask, what do functionals kill if you just look at them on homology? What functionals kill? They kill precisely the torsion. So this is a theorem. It's called the universal coefficient theorem. It says that if you go dual somehow, you don't lose too much, you just lose torsion. Okay? This is in 10-15 minutes what you need to know. Okay? So of course this is just almost nothing, but I think it's a few words anyway. Now Betti knew all this. Betti, by the way, so there's some interaction between Riemann and Italy. You know, Riemann died in northern Italy. He had tuberculosis, and he thought he could go and survive tuberculosis in the good weather. I think at Lago di Garda, one of the big major seas in the north of Italy. I've never seen his grave, but he went there. He's a friend of people like Betti. So they knew about this stuff. And Betti, there are numbers named for Betti. So they're called Betti numbers. And they're the dimensions of the homology. So the Betti numbers so BK. So let's make these things vector spaces so that you have no worry at all about the torsion and all of this stuff. For example, the Kth homology with coefficients and real numbers, for example. These are the so-called Betti numbers. These are vector spaces, and these are Betti numbers. Okay. And now, so, at the beginning, who asked this question? I guess Mihai asked this question. No, Sentao asked this question. You asked, you forgot your question. So, what does it mean topologically? This is,
I didn't ask any questions today.
oh, not today. Somebody asked the question, what does it mean topologically non-trivial and so on. So we are dealing here with the question somebody asked about Mihai. X is P2C. Okay. So the first question you will ask is, what is the homology of P2C? So the weakest question you can ask is, what are the Betti numbers of P2C? So the question is, what is the homology of P2C? I will tell you how to compute it, and then I will tell you what it is. You compute it most easily using something called Meyer-Vitor sequence. It's fundamental. Just remember that name and then think about it both in homology and de Rham cohomology. De Rham cohomology is dual to this by integration. You know about de Rham cohomology. So, yeah. So I will explain. There's a long exact sequence, which I will explain just in pictures here for P2C. Here's P2C. P2C is the union of two sets that I like. I will call U0, this is Z0 not equal to 0. And let's say I'm going to have a new set that I'm interested in. Let's call it W0. That is a tubular neighborhood of Z0 equals 0. So let's draw the picture. So this is always in my picture, Z0 equals 0 is back here. And then the rest of it is C2. So let's say the yellow thing here, this is U0. So I mean, this is U0 is the yellow thing. Okay? U0. Now, how's your intuition? You see it in U0. Do you see the unit ball in U0? The unit ball in the complex plane. Okay? Do you see a great big ball of radius a trillion, or radius the debt of the United States? So a great big ball will look something like this. Well, it's hard to draw. I'll draw like a ball, but it's, okay? That's a great big ball. And now I take the complement of that ball, and I consider the complement of that ball as a tubular neighborhood. It's a tube about, this is a tubular neighborhood. I can make it as big as I want. So it could be a very small tubular neighborhood about Z0 equal 0. So let me draw this equal. Okay. So let's look at this thing. This thing is topologically trivial. It's topologically completely trivial. It's a cell. So all these things vanish. You can retract it to a point. Retraction doesn't change the homology. That's part of the theory. This is topologically trivial. Okay. This tubular neighborhood of infinity, I just told you how to understand it. Make a great big ball, but I'm just going to push that thing to ball, and you see that contracting down on infinity. You see it? Just make this radius larger and larger, and it contracts down here. So this is topologically equal to P1C, because you can retract it down to P1C, and that doesn't change its homology. Now, the trouble is these sets intersect. So somehow you have the topology of that and the topology of that, and then there's some relation. You might believe somehow there's something going on, you worry about the relation. So you have to understand what this thing is. Right? This thing is a great big ball. Well, let's see. The great, what is going on here? Maybe I draw the picture so you for sure understand it. This will be green because it's good. And this is green. Not very didactic. But this intersection, of course, this is U0 and that's W0, so this intersection is key. Right? It's the tubular neighborhood minus the P1. Right? Well, that's retractable to the sphere. Right? That's retractable to the sphere just by taking the radius and shrinking it down to the sphere. That sphere is dimension, this is P2, so that's the unit sphere, and it's dimension 3. So this is S3, topologically S3. So, topologically trivial, well known from before, so we're going to argue recursively. Sphere, we have to do something for the sphere. Similar argument, and you could compute then the Betty numbers of P2. It's easy to see, it's a formal point, that B0 equals B4 equals 1. We've seen it in our course last semester. This is the top dimensional thing that's really in dual to that is the orientation form. This is just the fact that this is just a point basically. The I cohomologies are 0. This is also easy to see. And the interesting thing is B2. It's easy to see that the odd cohomologies of at least B1 because for example, you can see the homotopy is 0. You just take a circle someplace in here, and a circle in here can be moved away from this P1 at infinity by smooth movement, because it's codimension 2, and then you land in a cell, and then you homotopy at the 0. So it's very easy to see B1, and then for similar duality reasons, B3. B2 is 1. Okay, and you buy it. I mean, you're willing to buy it. You can see the thing that's playing a role back here is this thing at infinity. That's the thing that's generating topology. And in fact, so that means that H2, P2, C, let's say over with integral coefficient Z equals Z times the generator. And what that is I'm going to write it here, Z times the hyperplane, and the class of the hyperplane, and this hyperplane I'm calling H. It's really a copy of, I call it hyperplane because it's codimension 1. So the generator of the second homology is really this thing back here. You understand what I mean, generator? It means you can just, this whole theory of singular homology, I just map this thing in. I mean, it's not some fancy business, it's just you map this. There it is. Okay. This is elementary. Everything I said to this point is just an elementary exercise in elementary topology using Meyer-Vietoris sequence. Meyer-Vietoris sequence is the thing must be good. I think Vietoris lived to the age of 117 or something like this. But he was Austrian. You see, he walks around the mountains. So that is a small detour into topology. And now what does it mean topologically non-trivial? It means that if you have a surface in P2, it means its homology class is non-trivial. Okay. So if you have a surface in P2, surface, it has a homology class. So this gives you a homology class, which using this description of homology is an element of Z. And this number is called the degree of the surface. Okay? Now you'd be very happy to know if you have a polynomial equation of degree D that the surface it generates topologically that degree. Now, you shouldn't ask these questions because it takes me half an hour to answer. But I hope it motivates you to study homology theory, cohomology theory, and then the higher levels. I think a modern book, which looked good to me, I have not studied it, but a modern book, maybe Kevin can remark on this, is the book of Hatcher. It is, contains everything, and it is, I think, written for users, not...
Right, I mean, it has a lot of stuff in it.
It's got a lot of stuff maybe you want to disregard and so on.
No, but it's very good.
You would agree, it's...
Yeah, it has also a lot of pictures, which is
Yeah, I think it is a good thing. My generation, the Book of Spaniard was sort of a Bible. Up until that point, there were very few books because this subject is very new, believe it or not. So now I will answer your question. Okay. I will state your question again, but in my way of saying it, and I will answer it with a trivial answer plus a conjecture of Tom, I don't know how to pronounce it, René Thom, plus the answer of the Thom conjecture. This is very interesting. friend Stefan Nemirovsky for making this clear to me, reminding me of this Tom conjecture and this interesting theorem. So the first question is, does every surface have smoothly live in P2C? This was your original question. And the answer is, I've answered it already. Yes, because you can put M in R4, which is equal to C2. Well, the real question is, given, does every, for example, I think I asked this question, does the surface of genus 2, as an example, live topologically non-trivially in P2C. Okay. So that means that this class is of a given degree not equal to 0. That means this topological class of a given degree is non-zero. The answer to this question is a little bit embarrassing, but the answer to this question is trivially yes. So the answer to this question is trivially yes. And here's how you do it. You take a complex curve, say the Fermat curve, see this, let's call this this curve C. As we all know, this has genus 1. This has genus 1. This is the curve C. Now, the topologists who immediately answer any question like this are all surgeons. They do surgery. They don't just do topological surgery, they do smooth surgery. And, of course, any topologist will laugh at me and say, well, I take a point here, I take a coordinate chart here, I take a really tiny little tube into this, and I smooth it out into here, and I add on a torus that's inside of this coordinate chart. See, that was my point here. You can put it inside of a cell, and then there's topologically nothing going on. Again, if you do surgery inside of a coordinate chart, you can hook on a torus onto a torus and get a surface of genus 2. So the answer to your question is yes. Okay? Even this question. Okay? So what you did is, this is a very remarkable thing. What you did is, you start with the elliptic curve of genus 1, of degree 3, you add on something, and it's still of degree 3, but the genus has gone up. Right? Okay? The Tom conjecture is that you can, for example, have a surface of genus 2, but is in a higher, could you have in a higher homology class? Do you understand what I'm saying? Okay? Could you have a surface of genus 2? So here we had a surface of genus 2 in degree 3. And the way we did it is just by adding on something. But somehow, if you put it in a higher homology class, you're going to have to subtract off something, because a higher homology class might have, if it's a complex curve, it's going to have a very high genus.
But which higher homology? I mean,
Higher degree. So let's just make it precise. I don't want to write. Let's take degree equal to something I understand. What did I say yesterday? How do you get genus 10?
It's 4.
4? No.
Yeah, because it's just
4 times minus 1 is 3 minus.
Oh,
I think
6.
6.
5. Really?
It was 6.
I think 6. I think 6. So let's take degree 6. I think this. I don't know. Let's do it. Okay, so you have genus 10. Okay? So I'm interested in this degree. So if you take a complex curve in this homology class, it's going to have genus 10. Right? A smooth complex curve, not singular. Smooth complex curve in this homology class is going to have genus 10. So you do this. I don't know. You have 10 handles. There it is. Okay. Now, if you do this silly surgery, you can add on little tori and do stuff here, and so you can push up the genus and have the same degree, the same homology class. The question is, then, the interesting question is, what about degree of this thing equal 6, but genus of this thing equals 2, for example. Low genus, high degree. Now you understand. Conjecture, René Thom, it doesn't go. Answer, it doesn't go. This is a theorem proved maybe just a few years ago by some people I know. So it's a very deep, interesting thing. Isn't that fascinating? So your question, the naive question, is trivial, but if you think a little bit further, the non-naive question, which is pretty obvious, can you do it in all degrees? You can only do it if you make a trivial surgery to increase the genus, but you cannot somehow make it go down. That shows you how tautologically non-trivial this thing is. I mean, it's very remarkable. Okay, that's the detour of the day. Well, let me do one more. So this morning's lecture is a lecture on what can go wrong, how delicate things are, maybe. So the next remark is more on the difficulties caused by singularities. Naive idea if the codimension of some, depends where we are, but let's be abstract, the codimension of some set that's a reasonable set, analytic set. Yesterday we talked about locally defined by Ullmann functions or something like that. So we would be very happy if the codimension is 1, then A can be defined by one function. then there's a really good, maybe it's almost a unique function, right? You can normalize it somehow and so on. So there's a very good relationship between sets and functions. Codimensional one-to-one function. This is true, obviously, I think, for manifolds.
But A has to be smooth.
No, if the ambient space is a manifold, there's no obstruction. So A is I didn't say this here, so A is an analytic set. So locally defined by holomorphic functions in the ambient space X. So one. X. So if X is smooth, the answer is you can do it. You might smell algebra here, right? Because you're talking about the ideal of functions which vanishes on A, and you would hope that that is a principal idea, right? That's basically what you're asking here. If you have a one codimensional set, is the ideal of functions that vanishes on A principal idea? This is true for manifolds, so it's true if X is smooth. It's easy to see. But it is very false in general if X is singular. So in dimension 1 is not so interesting, but already in dimension 2 is interesting. So let me just close the lecture today with an example. You will be shocked at the simplicity of the first dangerous example. Let's let X equal, I'm going to do this in an affine way, so we're using the affine coordinates. I'm going to find the most obvious, I'm even going to give you letters that will make you understand what this thing is. So, in the back of your head, I hope you look at the determinant equation. Turns out the equation determinant equal to 0 is a non-trivial equation. This is a homogeneous polynomial of degree 2 in affine space. This is a cone in affine space, so as usual, I draw this as a cone. This is X. And the dangerous places I always try to do in red because a fire is burning. Obviously, this is a singularity. This is the only singularity of this thing. Just check. Okay. Now, you do something about the simplest thing you can think of. Consider A. So let's say not A, but let's say first of all B, which is equal to Z1 equals 0 in the cone. Okay, in the cone. Now 0. So if you wish, I'm going to draw a completely naive picture. So here's the cone. And here's this dangerous point. Okay. And now this thing's a plane. I mean, come on, it can't be, it's the simplest thing possible. So this is some plane that comes here and intersects the cone somehow. first I'm going to draw the wrong picture. So somehow there's a dangerous point, and okay, so it intersects it somehow. B. Okay. Well, I mean, it doesn't take a genius. You don't need to be a minuto and think about the local ring here or something. All you need to do is to say, well, if Z1 is equal to 0, and you're in this cone, then it means that either Z2 is 0 or Z3 is 0. Right? In the cone. That means it has two components. Has two components, what did I say? Z2 equals 0 and Z3 equals 0. Okay, so the way this looks, if you think about it for half an hour, just to no, maybe you have to think about, I had to think about, you're much quicker, I had to think about this for a day. Yeah, because nobody told me what to do, but I'll tell you what to do. Of course, that picture is completely wrong here. I mean, you can't understand it from that picture. But you can understand it a little bit if you look at my picture. The correct picture is the following picture.
But it's really hard to visualize. I mean, although Z1 equals 0, it's one-dimensional complex space. It's like a plane.
Z1 equals 0. Is Z1 equals 0 in the cone or in C4? It's a three-dimensional plane, three-complex-dimensional plane. Okay, so it intersects the cone in the two-dimensional subvariety, right?
Okay.
Right?
So how do you draw the line? I mean,
I will show you.
No, because I mean they should, like, if B is just that line, it cannot be like that.
Huh?
B cannot be just that line because
No, B is in fact two-dimensional. So
yeah,
I mean,
that's the thing.
but you're talking about like my student from Cameroon who wants me to draw these pictures precisely. I can't do it. But I'll come close now. I'll come very close now, okay? To do this, I want to tell you something else. This is beautiful. This is incredibly beautiful geometry. And it's even related to representation theory. To do this, I want to explain and now I probably have forgotten the Italian. You know, I'm somehow Italian from a mathematical viewpoint, and then I forgot the Italian. I think I want to explain the Zegri embedding, and I apologize to my Italian teachers, whom I love dearly. This may have been Veronese. Embedding, but I think this is really the Zegri embedding. I think it doesn't matter. Of P1 cross P1 into P3. I'm going to explain this embedding. Okay. So as a quadrant. Exceptional case that the two-dimensional quadrats in P3 are really products. It's very rare. So P1 cross P1 has homogeneous coordinates, let's say Z0, Z1, and W0, W1. And I'm going to take those to the following thing. Z0, W0. This thing, maybe Elitza will tell me, I mean, this appears in representation theory all the time. So you have the SL2C cross SL2C representation on the product of P1s, and then you get it on this quadric. I'm going to talk to Lie group specialists. The group here is, as you know, the SL2C, and the group here is SL2C. I'm going to get it acting on a quadric here. Okay, a quadric, by the notion quadric, is a quadratic form. So it goes into SO4C, and as everybody knows, at least at the Lie algebra level, those two things are the same, and that's exactly what is happening here. So the mapping is Z0W0, Z0W1, Z1W0. I mean, you do the most stupid thing you can possibly do. Z2W1. What did I do? What the heck did I do? Oh, I'm sorry. Z1W1, right? So you put all the cross monomials that you could, right? And of course you see that you got to make sure that not all of these things are zero, but you just check since one of the two things here is not zero and one of the two things here is not zero, then not all four of these things are zero. And this is a wonderful quadratic embedding here from P1 into P3. Now you can have fun. I'm going to draw P3. I'm coming close to drawing your picture. So here's P3. Now I'm still that's okay. The equation of the image. Now you're going to be really happy. So P3. Let's see here. The P3. I'm going to write homogeneous coordinates Z1. I'm going to leave Z0 out here for a minute. Just homogeneous coordinates in P3. Oh God, are you crazy, Al? Wait a minute. Zeta 1, Zeta 2, Zeta 3, Zeta 4. I'll start at 1 here just for fun. And the equation here for the image, you can just check it. These vectors are linearly dependent. The equation here is, well, I may be wrong up to the order here, but I think it's really even right. Zeta 1, Zeta 4 minus Zeta 2, Zeta 3 equals 0. Is that right?
Yes, it is.
Well, that's my equation. That's my original equation. But my original equation is affine. Right? So this equation is here. This is P1 cross P1, which is, of course, justifiably written as a square. Product of two lines is a square. Now, here's the origin in C4. So don't forget, if C4 is a cone over P3. So here's the origin in C4. If I write it in affine coordinates, there's 0. Now I have the cone. Now I have the cone. I'm sorry, I'm going over, but this is so beautiful, I have to do this.
You're not over.
Huh?
You're not over.
Oh, okay, good. Here's the cone over this thing. And if I've been better at drawing, let me get a little bit better at drawing. So you can see it better. Maybe I put the origin here, and I draw it. So here's the cone over this side, and here's the cone over this side. That's one side. And there's another side. Maybe I'll put another side. See, the cone over a line, you know very well, that thing is really a product, and that thing is embedded as a line, and a cone over a line is just C2. It's the usual cone over a projected line. So this thing here is C2, and this thing here is C2. It's a beautiful smooth manifold through this singularity. And this cone over the line, as you see, you can easily check what those faces are. Those faces are exactly B together. So this will be Z2 equals 0, for example, and this will be Z3 equals 0. Okay? Okay, so that's the picture, and that's what's wrong. I will tell you, from the point of view of global geometry, what is wrong. If you remove this copy of P2, that's one of the faces, and claim that this copy of P2 is given by one equation, then the complement will be affine. But in the complement, there are many, many curves. That cannot be. So that's a geometric contradiction. If you could define this by one equation, that would mean the complement of this thing is affine. You could check it. But it cannot be affine because it has many compact varieties in it, namely violating the maximum principle. So that's a very interesting argument. But since maybe you like formal algebra, just simply check that this cannot, in the local ring, that this cannot be defined by one function. What does that mean? So the ring here, the local ring, so the ring of holomorphic functions on the cone, or algebraic functions. Let's do algebraic functions. It doesn't matter. On the cone is here, X, is, of course, the power series ring in 4 variables. Well, the polynomial ring in 4 variables, modulo the ideal of functions that vanish on the cone. So it's just simply what I wrote down. Okay? And then what you have here in this, what you define here by Z1 equals 0 is the ideal generated by Z2 and Z3. And you will see that there is no way that this can be generated by one element here in this ring. You just check it. Okay, it's a formal algebraic calculation, but then you have to ask yourself, why is this true? And I will tell you why it is true. The geometric reason why it is true is at infinity, it's very deep. At infinity, you have some compact varieties in the complement of this face. Okay? And you don't see them unless you really think seriously. So it's a deep thing that this face, you understand, I hope at least you understood what I said, this face, one of those components, cannot be defined by one function. Very, very interesting, yeah? Okay. So the word you keep in mind, the buzzword here is, this face is a Weil divisor. So this is Jean-Pierre, this is Weil in the sense of the French mathematician Weil. You speak, how do you say it? Weil. I believe it's the same name as violet in German. It's probably exactly the same name. And so is Weil. So this thing is what we call a Weil divisor. And it is not Cartier. Cartier divisors, I'm going to talk about this afternoon, are defined by one function. So this is the French mafia here. André Weil and Cartier, both members of Bourbaki. This kind of language was introduced there. This is a Weil divisor which is not Cartier. Codimension 1 which is not defined by one function. It's a very important thing to know exists. And it only starts happening really in a fundamental way in this dimension. Okay? So, in summary today is just the pathological problems caused by singularities plus the answer to your question on what surfaces go into P2. I think it's a beautiful subject because as you see we use everything.
I had a question about the naive idea. So if you have codimension 1, so using algebraic techniques, you consider the ideal and you check whether that's prime ideal. Algebraically you define. But I mean, is there any analytic way to pin down that function, if not explicitly, as a limit of certain function?
Well, that's interesting. So please say again. You want to pin down
A can be defined by one function. It's an analytic set, it's a zero set. You want to write it as a zero set of only one function.
That's right.
So
You want to define. You can't do it you can't do it analytically or algebraically, but you maybe you want to do it in some limiting process.
yeah, that's what I'm saying. I mean, of course, you don't expect that probably you just find out one function value whose zero set is this analytic set A, but probably, I mean, locally it is given by zero sets of certain number of functions, and
so in this case, 2.
So I mean,
Yeah.
so I mean, what I want to say is, I want to define A as a zero set of one function. Can that one function be obtained as some limiting process?
You know, it's a good question. I don't know. Let's think about it a little bit. I mean, it seems pretty obvious. Nearby, you think you can approximate this thing somehow. Yeah? But obviously you're not going to approximate it very well, because one way to think about approximating things is that you have a regular mapping whose zero fiber is this thing, the thing that you really want to define with one function, that you can't. And the nearby fibers are you're approximating sets. But you see, that's not, I think that's not going to work that well. It's very tricky business, and you may have, look, I don't know. And many of these great topologists, René Thom was one of them, was trying to understand this singular phenomenon in terms of real geometry. Maybe that's what you're getting at here. Maybe in terms of real geometry, you can define this somehow. Somehow over the reals in some reasonable way. I don't know. Okay, I'll try to think about what you mean. You also don't know what you mean, but no, I mean, we don't care. It's nice. Okay, yeah, thanks for your idea. When I discovered this example, it's a well-known example, but for me, it was an eye-opener that in such a simple situation, that these cones have this algebraic property. And this is a cone coming from representation theory. This is a cone over the closed orbit in representation. And this happens all the time. So it's not just some pathology, it happens all the time. Okay, thanks. So I'll see you this afternoon. Could we start 15 minutes early? Is that okay? Yeah? That's